There we go. All right, it is my great pleasure to introduce Thomas Koffel, who is going to be talking to us about a niche theory for positive interactions, which I assume is going to be in the theme of coexistence theory that we've had for the past quite a few talks on this series. Thomas is at Michigan State University, I believe, right now, even though, as he said, he's currently residing in Kansas. But oh well. I'd just like to ask everyone, please turn off your mics unless you are Thomas, and then with that, I will give it to you. So thank you very much.
Thank you, Yuri, and thank you guys for the invitation. It's just a great opportunity. It's a series of seminars. So again, I mean, this is great for theoretical ecologists. So thank you, and thanks everyone for coming. So today I want to present you a theory of positive interaction, trying to build a generic framework that can sort of like naturally embed positive interactions such as facilitation and mutualism. All right. So if we look at diversity of forms and function on the surface of the Earth, taking here the example of plants, we believe as ecologists that part of this diversity has to do with the different challenges these organisms face, right? More particularly, you can think of them as being related to the different environments they live in. So to study this relationship between the two, let's consider on one side our focal organisms and their diversity, and on the other one, the environment they live in. And by environment, I will use a broad perspective, putting together the climate, resource availability, the presence also of natural enemies, which can be unconventional for some. So it's part of like the biotic environment of my focal organisms. And importantly, these environmental factors tend to vary on geographical space along these spatial gradients. So for example, taking the example of Kansas, this gradient from west to east of increasing precipitation. And when you look at, for example, plant communities along this gradient, you see a pretty striking signature of this, going from short grass prairie to mixed grass, and then tall grass, and even a little bit of eastern temperate forest. And so this is the first like connection between the two, is the idea that the environment selects. So basically, life forms have to respond to their environment, which determines eventually through their requirements if they can grow in a given place. So the climate has to be, good enough. They have to be able to find resources and avoid natural enemies. And if you can quantify all these aspects and measure them, for example, with experiments in the lab, you could reconstruct this sort of hypervolume of these environmental factors that we call the niche. But often we forget that the relationship also works the other way. Organisms, by their activity and through their populations, do modify the environment they live in. So, plants deplete resource in the soil, but they also, through recycling, create soil. So there's like a dual idea of plant impact on the soil. Organisms such as keystone species maintain so for example, here the example of sea otters, they maintain the kelp forest they rely on for food. So at the end of the day, we have this back and forth between organisms and environment that make the problems more circular, more complex because of this feedback loop. So if we want to understand how organisms are found along these gradients, we have to fully solve for these feedbacks. And more importantly, these feedbacks are the core of many ideas in ecology, right? Competition can be thought as the way an environment, often sort of abstracted out, mediates interactions between organisms, like the Lotka-Volterra coefficients. You can think of them as being kind of the product of species impacts and requirements, and I'll get to this later. Some eco-evolutionary perspectives, such as adaptive dynamics, measure the success of a new mutant as the way that this mutant responds as an invader to the environment set by a resident population. And in ecosystem perspectives, we tend to sort of flip this around. People are interested in the way biogeochemical cycles, for example, are coupled through implicitly the role played by life in the middle, such as carbon and nitrogen cycles contents. Okay, so I will argue today that one of the sort of most natural sort of theory or framework body of theory to think about this relationship is what people have called contemporary niche theory. And it takes its roots to, let's say, Tillman's work, for example, who popularized the idea of this of competition being mediated by resources. So imagine two competitors, they share resources, and his work here came with this very appealing idea that if we know something about the environment these organisms share, so the resources and the way they influence growth, we can basically represent in this environmental space competition, such as competition for essential resources here. And so you can basically graph out species needs and solve it graphically to, at the end of the day, obtain community assembly. By this, I mean species exclusion or coexistence along these gradients of environmental supplies. Simon Levin also, in the same period of time, developed formalized the idea of the competitive exclusion principle around this idea of environmental factors. So if you consider here a set of species and you know that they interact through these environmental factors Z's here, and you don't really need to say much about what these Z's are, you just have to know that they're mediating these interactions. At the end of the day, you can potentially put an upper bound on the number of species that can coexist. And because this is very formal, it can be applied to resources, but also, for example, to predators. So imagine your focal species are sharing some natural enemies, okay, so such as my plants here and my slug and snail. You can think of them as mediating something that is very akin to competition. So Bob Holt developed the concept of apparent competition to encapsulate this idea. And finally, I think John Chase and Matthew Leibold really put together his body of work in its sort of generality around competition and apparent competition across these nutrient gradients. And very importantly, they tied all this literature around the concept of the niche. That was sort of a very broad concept, very important in the development of ecological ideas. And I think they really nicely put everything together in their book. And finally, again, I want to mention briefly that adaptive dynamics is one of the frameworks more focused on evolution, I mean, at the interface of the two, that sort of naturally shares a lot of similarities with what I just presented here. Okay, so let's step back and think a little bit about a general class of models that sort of is amenable to what I just showed you before, this graphical approach developed by Tillman. So what is the sort of general models we can apply these tools to understand community assembly along these gradients? So let's consider we have some species indexed by J here with abundance N, and they all have a growth rate here that is some function. I don't have to say much about it, except that it is a function of the shared environment. So there are no direct interactions. Everything is sort of channeled through the shared environments. And then if we look at the equation for the environmental factors, I will assume that they have a sort of intrinsic dynamic that is here a chemostat, a very simple intrinsic dynamic, that in the absence of any of my focal species, you see the value at equilibrium would be given by this E tilde here. And this E tilde is basically what we're going to call the supply. And it sort of quantifies my gradients, depending on the value I choose to work with. But then there is this feedback, and organisms collectively, through their densities, affect dynamics of EI. More precisely, to quantify this, let's introduce, following Giza's work with co-authors, let's introduce the sensitivity of species J for factor I by simply taking the slope here of the growth rate. So basically the derivative here along these different environmental gradients. So if you take the collection of the Sij's for a given species I, you end up having a vector that we're going to call the sensitivity vector. And conversely, you can do the same with here, taking this coefficient here and renormalizing it by the lambda. This is important to apply the graphical approach, but just think of it as, again, the impact this time of my species on the set of environmental factors. So it's going to be a vector that we call the impact vector. And I was telling you I can generate gradients by simply changing the E tilde here and solve for my feedback along this different E tilde. Okay. Is there a question? Okay. So what's convenient with niche theory is that we can, and what's the point of setting this as a general framework for like a general set of equations, is we can translate everything graphically. We can basically represent so if we take one species here, if we delimit the region of points of environmental factors for which the species can grow, we'll have a boundary here that is very important. It's called the zero net force isocline. It's the set of environmental factors for which my species can be found at equilibrium. And then what's convenient is that the supply points here, you can see they live in the same space as my environmental factors. They have the same units. So I can basically superimpose them in the same graph. And this is a bit of the nuts and bolts of the graphical approach. You can basically combine the information you have on the impact vectors and the ZIMI to basically solve for, if I give you one supply point, you can construct what's going to be the environmental at equilibrium and know everything about your system. So there's a way to associate supply points to equilibrium that basically result in solving this feedback loop and know something about the equilibrium of your system. This actually, so if you do this one species, it's a little boring. You just get at the end of the day that my species can be found in this area. But if you take several species, it gets more interesting because you can basically study competition. You can perform like a graphical invasion analysis between different species by excluding equilibria that's going to be stabilized by the invasion of the other one. And at the end of the day, you end up having region where you find one species or the other one, or they coexist. And from there, you can extract the realized niche now of my focal species 1 here. So in the end, you can see it's a classic result of competitive system. The niche of my species has shrunk because of the presence of the competitor here. Okay, so what now happens when we have positive interactions? We know nitrogen fixers and hence in the soil, there are nurse plants, there's like pollinator mutualist systems, or even introphic systems. You can think of, for example, here, sea otters as being mutualists with the kelp. By consuming urchin, they facilitate growth of kelp, and the kelp does the opposite by feeding urchins. So what happens in this sort of general realm of these positive interaction, indirectly mediated positive interactions? So first, we're going to look at positive interaction in the context of the fundamental niche. So when we have only one species, we'll move on to the realized niche with several species. And eventually, I will show you some ideas about how to extend our understanding of the definition of niche difference in the context of these positive interactions. So let's jump to the situation of a single consumer here with density n, so one species, and an environmental factor, like a single environmental factor. And I was just telling you, there's basically two things we need to know: the impact, and we need to quantify it, and the sensitivity. If we're to look just at the sign of these two vectors, I mean, the two numbers, in the case of a single environmental factor, following Estrella et al., we can basically decompose this into 4 possible outcomes. So either you can feed an environmental factor that is detrimental to you, that's a predator, or you can consume something that's good for you, that's a resource. But we know that both scenarios here lead to something that is basically competition or regulation if there's a single species. What happens in these two other corners? We have, following loop analysis, we know that minus minus will lead to a plus sign, and plus plus will also lead to a plus sign. So in these two situations, we can intuitively guess there's going to be some instability associated with a positive feedback loop. And what I want to show is two things. I want to show first some ecological examples where this can happen, and then I'll show you what the consequence for the niche is of these positive interactions. So let's consider first an inhibitory resource. So basically at low density, my microbe likes this substrate, but when it reaches a certain maximum here, it suddenly turns like detrimental to growth. So we can formalize this using a simple set of equations. And the first question is always, what is the set of environmental conditions that allow my consumer to be at equilibrium? In 2D, this is the zero net gross isocline. If you only have one dimension, basically it's an R star. And we find indeed an R star in the system where basically my population is correctly regulated as a consumer. But however, there's a second point here, a second intersection, as you can see, where things are a little weirder. As you can see, the slope here is negative, which means that in this situation, sensitivity is negative. So this is not a resource in this example. It is something that is detrimental to your growth when it increases. And so this leads to this positive interaction, okay? So what's the consequence of this RC here for the niche of my consumer? So let's look at the consumer density along my substrate supply. And not surprisingly, you can see that basically above RC, there's a region here where I get alternative stable states between my consumer going extinct or my consumer persisting at high positive density. And they're separated by here an alternative stable states between the two that is associated with this unstable regime here around RC. And if we're to use the niche concepts to formalize this, let's follow Bob Holt's ideas and call the set of supply points here where invasion is possible the establishment niche or the invasion niche. So it's going to be between R star and RC. And then the persistence niche, which is the set of supply under which my species can be found at equilibrium and stably, at least locally. As you can see, these two concepts do diverge in this context because of the positive, the alternative stable states. And so basically we have a new sort of niche that appears that I would call the Allee niche with a reference to the Allee literature, where basically species can collectively, so my consumer, if there's enough of it, it can collectively detoxify when there's a lot of resource in the system and bring the supply, the resource availability at a level that's bearable and be properly regulated. But if you start at small densities, the system is too toxic and my population goes extinct. That's basically what's happening in this region of Allee niche. Okay, let's now move on to the second example, facilitation by nitrogen fixing species. So let's consider now two limiting factors. There's nitrogen and phosphorus, so it's a classic Tillmanian-like setup. But now we'll assume that some of my species will be able to fix nitrogen up to a certain rate that's given by this maximal rate F. When soil N is too limiting, they can sort of switch to N fixation. And because there's some recycling in my system, some of the nitrogen sort of ends up being reinjected in the loop, and this can lead to these feedbacks, as you see. Let's further assume there's going to be a trade-off. So if you're a good fixer, you're kind of bad at getting phosphorus. And we'll consider three species: non-fixers, facultative N fixer, so they can only partially supplement their needs in nitrogen by fixing, and an obligate N fixer that can persist on any level of nutrients, doesn't really rely on soil N because it can fix anything it needs. And the first question is going to be, what is the fundamental niches of these three species? So now we have two gradients, nutrient and phosphorus availabilities. So it's going to be like a classic 2D niche setup. And we recover for the non-fixer the sort of classic L-shaped zero net gross isocline. And as you can see, the impact vectors are all pointing down, which means that basically the N fixer is consuming both nitrogen and phosphorus. Okay. Now, what happens with the facultative N fixers? Things are a little more interesting in this situation. Basically, there's still a minimum amount of nitrogen that's necessary in the soil for my N fixer to invade, because again, it cannot fix as much as it wants. It relies partly on N in the soil. So there's an N star here for nitrogen, below which my N fixer cannot invade from small densities. But as you can see from these impact vectors, pointing up, the net effect under low nitrogen availability of my N fixer is to enrich the system in nitrogen. So basically, through fixation and recycling, this nitrogen fixer puts more nitrogen in the soil that it took. So in the end, it's like feeding, it's basically enhancing the resource it is consuming. So it's an example here of the opposite scenario. And these together, again, leads to a region of Allee niche that can be very easily reconstructed like naturally by using the graphical approach. And in the end, I just want to show the example of the obligate N fixer here, that there's no minimal amount of nitrogen it needs. And interestingly, even though there's a strong positive feedback on nitrogen in the soil, as you can see, there is no Allee niche in this example. So it's a bit of a counterexample. There's no alternative stable state in this setup. All right, so the answer in short was that positive interactions within species can lead to the expansion of a species niche into a region that is where the species can persist, but it comes at a little bit at a cost, because this is an Allee niche region, which means that if a perturbation brings the population density below the Allee threshold, the population will eventually collapse in this setup. So there's a bit of a cost associated with this expansion of a species niche. Okay, what happens now with the realized niche? So let's again consider my nitrogen fixing species, and I'm just going to show you what happens when I grow my species together. So what happens to the niche of the non-fixer in the presence of the obligate N fixer? And as you can see here, we get something that looks like this, where basically the niche of the non-fixer has been expanded by a region where it actually coexists with the obligate N fixer. how does this work in practice? So this is kind of classic. It's been described verbally in the facilitation literature, but it was nice to get it working with a sort of nutrient explicit model here in the context of the niche framework. How does this work in practice? It's pretty simple. For a supply point located here, so outside of the fundamental niche of the non-fixer, basically the obligate fixer will invade first. And as it invades, as you can see, the nitrogen availability in the system increases, which eventually allows the non-fixer to invade. And when it invades, they eventually coexist together at equilibrium. But things don't always happen this way. So if we take the facultative end fixer and you grow it with the obligate end fixer, you see that the niche is modified in the following way. And don't necessarily look at the red region here. Let's just focus on this sort of triangular shaped region here. So in the fundamental niche, this is part of the Allee niche of the facultative end fixer. But now, because there's the obligate end fixer in the system, my facultative end fixer is able to invade in this range of supply points. Again, if we were to look at the time dynamics, things work kind of the same way. The obligate end fixer, let's say, imagine this propagule presence, there's some seeds, so it's there, it invades, it grows, and the facultative end fixer cannot invade even though it has seeds in the system. And so again, facultative end fixer can only invade after invasion of the facilitator because nitrogen levels have gone up. However, what happens when the facultative end fixer gets in the system, that the levels of phosphorus are drawn even lower. And they are actually, this is unbearable for the obligate end fixer, which eventually collapses and is excluded from the system. So this is kind of interesting because the facilitator in this case played just a transient role. So it facilitated a species that didn't really pay it back because the species excluded the facilitator. And so at the end of the day, if you look at a system that has been assembled through these transient dynamics, you would have lost you wouldn't see the obligate end fixer at the end of the assembly, even though it was necessary for the assembly. So it's kind of an interesting situation from that community assembly perspective. And if you're interested, we sort of extended this approach in this paper by considering a lot of species along a trade-off, so a whole continuum using a trade-based approach of very strong fixers and very good P competitor that don't fix much. And when you do this, you can apply adaptive dynamics to look at the successive invasions of these different species and how together they can create this sort of very ordered successive sort of suite of invasions that mimic facilitation driven by succession driven by facilitation and ecosystem development. Okay, so let's move on to another system where things are a little more symmetrical. So imagine you have two bacteria that are cross-feeding, which means that my first bacterial population N1 here grows by consuming R2 and N2 grows by consuming R1. But each population of bacteria also synthesizes in their cells the other nutrient, assume these are amino acids, let's say, resources, say amino acids of nutrients. And they excrete, they have some leftovers that they excrete in the system. So N1 creates R1 and N2 creates R2. So basically these two species are coupled. Each one creates what the other one needs, okay? So that's why we call it cross-feeding. You can write it down again, following a sort of a classic, something that fits in the general like niche model I was saying you in the introduction. And here are the two terms here to describe cross-feeding, S1 and S2. And notice that so these two amino acids can be so synthesized by my two species, but they can also be supplied externally here by, let's say, the empiricist in the system, okay? And so the question again is going to be, how do these two species assemble along my gradients of supply of amino acids? And so if you look here in the first example where we imagine there is no synthesis, so basically they rely purely on what is supplied externally, we have two species that are basically independent. So we'll find the two species to coexist in the square region here, where there's enough of both nutrients supplied above each species R star, okay? However, if we start having some cross-feeding, the region of coexistence expands. As you can see, basically this whole region corresponds to the two species coexisting, which means that if we look at this area, for example, N1 didn't used to be able to persist there in the absence of cross-feeding, but thanks to cross-feeding, now you can find, sorry, N2. So now N2 here, this is now part of the realized niche of N2. This is part of the realized niche of N1. So it's an example where there's been niche expansion of both species due to mutualism. However, if we were to go too far, so if our species are too efficient at cross-feeding, you reach a point where like you can sort of see geometrically that here these are the supply points, and these are the combination of supplies if you sum up each species, impact vectors. So if you sum up each species impact vectors and take a sort of a linear combination, overall here you have a situation where overall the effect is consuming, but here overall, if these impacts get too strong, this angle becomes open and these arrows are pointing outwards, which basically means it's kind of back to what I showed you with a single species. This is a situation where the two species collectively enrich the amino acids more than they consume it. And so this is going to lead to a positive feedback, but this time at the pairwise level. And so if you were to take a supply point here that is located at 0, so no external supply of my amino acids, we get again a sort of Allee effect situation where the cross-feeding pair either collapses or can blow up to infinity. Obviously, blow up to infinity never really happens in nature because your amino acids, at one point they will stop being limiting and something else will kick in. So imagine it's like sugar, like R3, that eventually becomes limiting. You can, so then you're adding a limiting factor. So you have to work in like 3 dimensions with like 3D thingies. So that's what we did in this paper. And at the end of the day, you end up having like an upper bound on how far your species can blow up, which eventually stabilizes here the cross feeders. Okay, so to conclude, how do positive interactions affect the realized niche? And the message is basically that species can expand the niche of our species, and we can use a graphical approach to investigate this. But also, this can sometimes happen in sort of less intuitive ways, such as the situation where my facilitator got excluded after the facilitated species got in the system. Okay, so let's move on to the last question. How do we sort of quantify these positive interactions using ideas like niche difference? So how can we do this? So if you go back to the cross-feeding pair, you can sort of see that if we think that the extent of the coexistence region tells us something about how stable how stable coexistence is, you can think that the angle between these impact vectors here, which basically describes the breadth of this coexistence region, can tell us something about coexistence and can quantify niche difference. And with the same situation here with my facilitating species and the facilitated, you could also imagine that if you were to measure this angle, maybe this tells you something about coexistence. And these ideas have been are pretty old in the literature, like Vitritis described this in one of his papers. And more recently, Saavedra and co-authors suggested that measuring these angles, this time on node-covered terrace systems, can be a way of quantifying niche difference. So let's try to do the same with niche theory. So let's just take a situation where we have 2 species that have perpendicular zero net growth isoclines. So they have like orthogonal sensitivities. But let's play a little bit with the angle between the impact vectors. And we know that if we decrease the angle here by having more and more overlapping impacts, we know that the coexistence region basically shrinks until this angle is equal to 0, and coexistence is basically impossible, except if you look at it right at the edge here of this on the impact vectors, right? So this seems to be right. The angle is a good measure of niche difference, and we know that when niche difference turns negative, we have kind of the opposite. We have alternative stable states, priority effects between the 2 species, which is kind of the opposite of coexistence. But we can do the same the other way around, right? We could just start increasing this angle, and as it increases, we recover the classic mutualist regime I was describing earlier, until we hit a point where suddenly mutualism becomes too strong and is locally unstable. So in some sense, we can smoothly move from priority effect all the way up to unstable mutualism by simply moving this angle. And this seems to be a good way of measuring niche difference. With the coexistence region here, so basically we have stable coexistence only between 0 and 180 degrees. And depending on which side it is from 90 degrees, you get either competition or mutualism. All right. However, so this situation was fairly symmetrical, right? And I took these zingies at right angle. But if you were to use a sort of a more generic situations, you would have an angle between the zero net growth isocline, which is the same thing as an angle between the sort of sensitivity, vectors. You would have an angle as sort of an asymmetry encoded by theta. You could have the impact vectors twisted relative to the zingies. So this is a kind of a broader context for this. And when you do this, you have to basically consider the angle between the impacts and the angle between the sensitivities in combinations. And when you do that, you can sort of get sort of this diagram that sort of recapitulates all the possible outcomes that you can go through by varying these angles, right? So we recover competitive and mutualistic coexistence. But because here I'm in the asymmetric case, interestingly, we also get a regime of one-sided facilitation here, where one species benefits from the other, while the other one is sort of detrimentally impacted by the first one. And so this sort of enables us to brush the whole spectrum of potential behaviors with these two metrics. And here, I don't have a lot of time, so I just mentioned that you can also superimpose here you can combine these two metrics into a single one, basically by using Saavedra's ideas on the local system. And so to do this, if you're interested, you can sort of map, at least locally, the niche theory model onto a local system. And if you do this, you basically get a mapping between the local coefficient on one side, and R, the growth rate, and the parameters, the geometrical parameters of niche theory. And when you have translated this model into a local system, then you can simply you can simply apply what people have been doing on the local system. That's what we did here. Okay, so to conclude, basically measure niche difference, I'm suggesting we could simply use species impacts and sensitivities. And this is convenient because there's no sort of, it works both ways. You can go in mutualism region and your metric is still meaningful. And I just want to give a few perspectives just to go through them rapidly, just to give you some ideas about more sort of exotic things we can do with niche theory. So the first one I was telling you is the case of carnivores. Here, my sea otters interacting with plants indirectly through herbivores. So this is something that can be asked in the context of niche theory. And I was telling you these are mutualistic interactions. If you just have to think a little bit about it, but that's what's happening. And you can apply niche theory, the graphical approach, to basically see that the plant is expanding the niche of the carnivore, and the carnivore is expanding the niche of the plant. And what's interesting is that you can even quantify the strength of this mutualism, this indirect mutualism, with these angles. So there are going to be some pairs of plant carnivores that sort of work better together than others. And I think this could be an interesting avenue for research. Another system we've been interested in was the gut microbiome. So let's consider bacteria in the gut that affect oxygen concentration. So this is carbon and this is oxygen. Mutualistic bacteria, we know they sort of fuel a pump that tends to decrease the amount of oxygen in the gut, which are conditions that they enjoy and that tends to be associated with healthy human guts. Pathogens, on the other hand, have mechanisms through which they kind of do the opposite. They disrupt these stabilizing homeostasis on low amount of oxygen, and they sort of fuel the gut into oxygen. So there's like an increased amount of oxygen in the gut that they actually enjoy and thrive on. So they sort of fuel their own expansion by doing so. This leads to basically a tug of war between the two microbes over the state of the gut, over the oxygen concentration. And so basically we've applied niche theory ideas to kind of study the resulting alternative stable states along gradients, either in like carbon uptake, so basically your diet, and oxygen concentration that can be modified with some sort of food supplements. And finally, just to show you, because if I don't show it here to an audience of theoretical ecologists, I never get to show this. We had fun with the graphical approach, and we mapped it onto adaptive dynamics by using this concept of geometrical envelopes. So basically, if you want to do this graphical analysis with a continuum of zero net growth cyclines, you have to take the outer envelope of these many thingies, and there are some analytical ways with calculus to do it. And when you do that, you end up having a theory of basically, you can locate ESS along nutrient gradients and map them to the supply points that give a birth to them. So the two frameworks are actually very intertwined and sort of naturally self-consistent with this kind of approaches. And we've applied this to study the evolution of plant defenses along gradients of resources in a context where they have to defend against a herbivore. And if you're interested, I can tell you more about this. Okay, so as a conclusion, I hope I've convinced you that basically niche theory is a generic framework to study diversity of interactions that lead to community assembly along environmental gradients, and that can quantify the strengths of coexistence along these gradients. I'm hoping I convince you that so the generality comes from historically thinking about resources, but also natural enemies. And in here today, I've tried to convince you that we can also move from negative interactions to positive interactions, and even from quantifying niche relationship from within, guilds to between guilds and traffic levels, such as this example here of these mutualists. With this, I want to thank my main co-authors on this project and co-authors that contributed on some of the examples I presented here. And I want to thank you all for your attention, and thanks my sources of funding. Thank you.
Thank you so much, Thomas. So now, as usual, if you have any questions, just use the raise hand button under the participant list, and I will call on you. Then turn on your mic and you can ask questions. Any questions?
Well,
Yes.
I have one, but I can't figure out how to raise my hand. So can I just ask the question?
Yes, but can you please wait a moment, because Jörg has raised his hand.
Yeah,
But
yeah.
you can ask the next question then after. Yes, absolutely. Okay. Yes, Jörg.
Yeah, sorry, I was just struggling finding out how to unmute me. So I find it super cool, this idea of like modern coexistence theory, which is like really focused on competitive two-species communities to expand it to positive interactions, also to trophic levels. And it all looks so like super clear in those examples that you've given. My main question is, I would like to also is like these two-species communities. It seems like this angle. Like for me, angle is mostly like a two-dimensional thing. Is it possible if I would focus on the entire? You talked about like you have a predator and the plant, and then the two herbivores in between. Can I also apply to the entire four-species community to understand how this four-species community coexists, and not only? It seems like you can either do the two plants or the herbivore and the plant. Yeah, you got it.
Yeah. Yeah, that's a good point. It is true. The way I frame things, it works better for interactions that are indirectly mediated. So there's something about you can quantify the effect of this other environment on the interaction between two species, and it works better when this environment is not the species themselves. Like you could frame things such as a species, you are part of your environment. I mean, you're conspecific could be thought as the environment, but things become a little circular and less useful when you do so, even though it's possible. Like you can think of a local system as, each other species. Like I think it's less useful, and so I don't think the angular approach would work in this context because of that.
Okay, and what if I had three species that are like that do not work circularly but feed on the same resource, for example, or? So
three species. So feeding on two resources, for example, so like more than two species, you're saying?
Yeah, I mean, three species on three resources you would actually need, but yes.
Yeah. So in this situation, so that's another great question. It is probably a limitation of well, let's say, so you can work in higher dimensions with higher angle. If things get more complicated, it's kind of the problem in most community ecology framework, right? Like with a lot of competitors, things get harder to study. So Savitra et al., for example, their angular metrics, they designed it for more dimensions. So they have a case where, they measure just the sort of the solid angle, right? So they get one number out of it, but in some sense you lose an idea about the shape of this. So if you imagine like three impact vectors, you could have a very symmetrical case, or you could have a sort of a flat on one side and expanded on the other one. And in that sense, the solid angle would give the same results for different shapes. So you lose some of the information on the way interact. So a single angle wouldn't encapsulate all the ways these species interact, but potentially you can do that. Then to sort of map more carefully my regimes, so the angle and the different scenarios of, they coexist or do they blow up, I think that would be harder to do generally, even though Gesine in the 2006 paper with co-authors, they have this suggest using the determinant of this product of sensitivity and impacts to get some information about the stability of the full system. But again, I think it's always going to be partial information. You cannot solve all the aspects of coexistence when you have more species, I think. So yeah, I hope this answers your question.
Okay. And then maybe if I'll add one last thing, when you talked about survey drive, it reminded me of like can we use these niche differences to also understand whether we have coexistence? Or like, are there fitness differences basically?
Yeah. So they used so I don't know if anyone has worked on this more precisely. So I don't want. But my understanding is that they use this. They focus on structural stability. So they actually they assume that if the equilibrium point is feasible, it's going to also be stable. And we know it's not always the case. So it's a limitation of this approach. It's again sort of only partial information. But if with 2D species, you can actually knowing which way this angle goes, you actually know if it's coexistence or priority effects. You can disentangle the two with the sign of this angle. But they also have like they do introduce this R here. They can plot the R, and then they have this theta angle. That's not the same angle I presented. That quantifies the fitness difference geometrically. So they also have a metric for fitness difference that we could as our system because we've mapped the two theories. We could potentially also apply it here to measure fitness difference in this context.
Okay, thanks.
Thanks.
Thank you very much. Sorry, David, were you trying to ask a question before you managed to raise the hand earlier?
Who are you asking?
Whoever was trying to ask.
Simon was the one who was trying to do it. So Simon, you go first. You're ahead of me.
All right, thank you. Hey, David, how are you? This is Simon Levin. So you kindly cited a paper of mine more than 50 years old on limits to coexistence. That's a very much equilibrium-based approach, and if you relax that assumption and allow coexistence via fluctuating populations, as people like Armstrong and McGehee have shown, you can get more species. So my first question is the degree to which your conclusions depend on an equilibrium-based approach, and what relaxation of that would mean. And secondly, and related, you talked about successional species. So in a successional process, you get lots of species coming along, but they don't end up in the equilibrium. However, if you embed things in a spatial context, you might find all of those species continuing to exist by a kind of fugitive species strategy where they colonize and then get replaced. So can you extend your approach to include a spatial dimension, and how might that affect your results?
Yeah, that's a great question. I think it's the hard part. Like space is complicated. I think mostly with this approach, the problem is it works best with only a few environmental factors. So you want a very simple environment to work with. So talking about, so we mentioned fluctuating environment. So imagine there's a nutrient that is supplied.
Well, I wasn't actually talking necessarily about fluctuating environments, although that's interesting. The fluctuations might be endogenous. They might be generated by the species themselves. Yeah. So some limit cycle or something more complicated.
Yeah. So I mean, I don't know. So I haven't thought about the endogenous fluctuation. In some sense, I think the way to fall back on our feet is to say that basically, when a resource is fluctuating, you cannot count it as a single resource anymore, right? You have to consider the different moments as themselves. So, I mean, that's one way to think about it, right? Or the Fourier transform or something like this have to be counted as separate. So I think that might be the way to keep this consistent, but I think the dimensionality of the environmental space rapidly blows up in this kind of context. And I think that would be sort of the same with spatial. So I think, I mean, maybe there's out there a theory of like, with a lot of environmental factors, where you can still use some ideas that are connected to this in these high dimensional spaces. I don't know. I would love to see something like this. That's the only. Yeah.
Yeah, Fourier series might not do you much good because of the nonlinearities.
Yeah,
in
okay.
the system.
Yeah.
But I know Chris has been using Cloquet theory, and that might be helpful.
Okay.
Okay. Now, Professor Tillman could go.
Oh, excellent. Thank you. Simon, if you go under reactions, that's where I found that raise your hand bar, and there's a little yellow thing on the bottom. I just discovered it now after 6 months on Zoom. So, well, I really enjoyed your talk, Tomas. It's wonderful ideas and wonderful advances. Just fabulous to see what you're doing. Simon gave you some challenges. I'll give you more. These two will take the rest of your career. But one of the mysteries I've had, it's within a trophic level of competitively interacting species. It's very easy to see how these sorts of trade-offs represented by these niches and the neat feedback effects you're adding to it can lead to coexistence of large numbers of species and explain lots of what we see. When I looked at the fossil record, I was amazed to see that when new species of herbivores and predators invaded brand new geographic areas, they invariably coexisted with what was there, coexisted for millions of years. And that suggests there's some other kind of trade-off that occurs across these trophic levels that is also very generic and very common in the evolution of new species. And I've not yet visualized a way to do it, but with your new approach, maybe you can answer this, what I think is one of the big unanswered questions about how the concepts of trade-offs and coexistence that we have a sense are pretty important among competitors actually scale up across multiple trophic levels. I'd love to have you solve that one and maybe explain it to me right now.
Yeah, I'm sorry, disappointing, but yeah, it's a good point. I wonder, I mean, some people have talked about, the only thing that really makes me think about is sort of broader level selection on some stability of some patterns, and some interactions are more stable than others, and so they tend to persist more than others, and so this leads to a sort of a selection of sort of like high level selection of some kind of interactions because of this stability, right? That if they tend to be more resilient, these assemblages would tend to persist and then sort of be beat other assemblages. So I don't know if this answers your question at all, but that's kind of things that I wonder if there's stuff out there on this topic. Yeah, that's, I think.
It is a little bit, it's one that I haven't viewed as being that viable, but it would be fun, Tomas, sometime Skype or Zoom one-on-one and just brainstorm a bit. It'd really be fun to hear more of your ideas. And also, if I could request, send me all of your papers you publish on this.
Okay,
it'd be fun to read all. Good.
Thank you.
Thank you.
Thank you so much. Bob Holt.
Hi, Thomas. Really great to see you. That was a very fine talk. For everybody else, Thomas took me out finding the rare and endangered Kirtland's warbler a few years ago in upstate Michigan, and I appreciate that. Hope you're birding out there in Kansas. I have a sort of a general question that's related to what both Dave and Cy asked, I think, and that is, why do we care about coexistence theory? I think at base, we want to understand what determines biodiversity on this planet at various scales in space and time. And so you could ask the question, if you didn't have these positive interactions, what would biodiversity look like, right? You can come up with scenarios where adding mutualism to a system will depress biodiversity. So you have two competitors that are to a degree niche partition, but now one of them gets a mutualist. What does that do? That increases the growth rate. That's to increase the competitive impact on the other species. And so voila, you might actually have fewer species at that trophic level than before. So I think one general question is the degree to which adding mutualisms and indirect mutualisms, as you have, so in such a lovely fashion, enhances or degrades biodiversity as a whole. So let's just throw that out as a sort of a general question for you.
Yeah, that's. I think maybe we can frame it using more of like fitness difference versus niche difference. In some sense, some mutualism can lead a team to be more powerful, right, which leads to exclusion. But if mutualism enables you to exploit a new niche, then you can stabilize, right? So I think I'm just repeating your question. So that's the way I would see the problem. Yeah, I don't know if this is like a generic. Yeah, I wonder. I don't know how I would address this question. I mean, probably with. Some people have looked at the assembly of sort of large food webs by taking a lot of species. I wonder if the literature on community assembly with random matrices using like the these physics tools. I wonder if they found answers to this, because they have. I remember they have models where you can tune the average. Yeah, it's not exactly a question, but they can tune the variability of interactions that they draw from a logical tourist system, and to draw sometimes some mutualism or more often some competition. And depending on where they put the average interaction, they have these diagrams of the sort of qualitative behavior of their assembled community. And I wonder if they have answers there. But it's not. It doesn't quite respond to the question about like indirect mutualism. Yeah.
Right. Well, great. Well, really fine talk, Thomas.
Thank you.
Thank you so much. David has another question, I believe.
You're muted, David.
No, David?
It builds on Bob's really interesting question. I wonder if the answer is that Bob is right in the short term, that you lead to displacement, but in the long term, you have a whole new suite of capabilities and skills. And so we have, for instance, this 150 million years of evolution of more and more diversity in the flowering plants, driven by the pollinator plant mutualism. The same thing when eukaryotes came into being, we had the massive explosion of the Cambrian in diversity on Earth with this new way of doing things, the eukaryotes versus the prokaryotes. So maybe in the short term, there's a cost, but in the long term, these innovations lead to a massive wave of speciation and increases in diversity.
Yeah, if I could follow up with that, Dave, I was just thinking over really long, macroecological, macroevolutionary timescales. Think about what are the implications of nitrogen fixation on this Earth, right? There's a classic mutualism. And if you didn't have nitrogen fixers, I bet the total biomass of the planet would be much smaller than it is at present. And we know there's some kind of rough scaling of biodiversity with total abundance of organisms. I mean, that underlies the species area relationship and lots of other things. So I suspect you're right that in the long run, these positive interactions have boosted biodiversity despite these possible short-term effects.
Yeah, I'm not sure. I mean, I think it's interesting that, well, like flowering plants, they basically took over, except they left a few niches for more primitive, even though I know phylogeneticists don't like the word niches, but so I think at one point some innovations with mutualists tend to be so good that basically you need them, everyone needs them, and when everyone has them, you're back to the start, right? You have to compete in other ways, and so I think mutualism leads to, again, sort of at one point everyone has to have the mutualists and work that way if it's the efficient way of doing it, right? And then competition happens between these teams of mutualists.
Okay. Are there any other questions? While people are thinking of potential other questions, I just wanted to say something which may or may not be helpful. But as it was mentioned, yes, there is flow K theory out there, which as you very well know, Chris likes to use, and which could be applied in the periodic case. Another thing that might help is that with Giza, a few years ago, we actually worked out how to do the Giza style niche theory in periodic environments.
Oh, okay.
Actually, the slide that you have right now on the screen is quite instructive. So what turned out is that the effective interaction matrix, your A, that one, exactly. So it's sensitivity transpose times, so the scalar product of sensitivity and impact, which you could also write as the sum over the regulating factors or the different environmental factors, as you called them, of the species I's sensitivity with species J's impact. Now, in the temporal case, it turns out that what you have to do is sum that over or in continuous time, integrate that over time as well, because your sensitivity and impact vectors are then time dependent as well, which is formally, in a way, just like adding yet another regulation index to your regulating factors. So, for example, if you had a bunch of regulating factors, say nitrogen and phosphorus are your two E's, two factors, then now each of those actually become regulating continuum. Nitrogen of T and a phosphorus of T that you sum over. Again, I don't know if this would really address this problem or if it's really in your in immediate interests or not, but it is out there. So
that's cool. No, you should definitely send me this paper.
Okay, I can do that. All right. In the meantime, have there been any? No more questions yet. But there's still a chance to ask. If there are no questions, then thank you again so much, Thomas, for this very interesting talk.
Thank you.
And for everyone for coming. The next talk, I'm actually not sure when it is, but Geza and Chris will tell me.
Right. I'm not sure about the pronunciation, you know. James O'Dwyer.
Oh, James. Okay. James O'Dwyer is next in 2 weeks then.
2 weeks, yes.
Excellent. Okay, so it's going to be James's talk. Thanks, Geza.
Yes, it's on cooperation, resource exchange, and stability.
Thank you.
So quite similar.
Excellent. Okay, in that case, thank you again, Thomas, and thank you everyone for your attention. And we hope to see you all in 2 weeks' time.
Thanks, everyone.
Thank you. Take care. Bye.
Great talk.